PLC control of equipment. PLC applications may be required to take some action or give some indication if a piece of equipment isn't doing what it should be. That's to say that something should be happening, something should be moving, and if it isn't, or if it isn't doing it in a particular amount of time, there is something wrong in the process. Okay, so proof of motion is needed. Non-movement may result in seized equipment, broken shafts or gears or belts. Motor could be disconnected and not operating. The power could be disconnected to it, or a piece of equipment could be overloaded. Using a PLC, we can detect movement. Movement is actually the change of a position. Movement happens over a period of time. Some rotating equipment uses pulse tachometers. Pulse tachometers does very much what we are doing with the striker on the end of the shaft, and they can be monitored by counters or timers. Timers can be used to monitor the time of an action or a movement. A timer usually is set to the longest period that action should take. Now, depending on the action, if it's a very quick action, the faster actions require a shorter period of time. Slower actions, consequently, take a longer period of time. If we need to time anything with a very short period of time, we can use an ultra-high-speed timer. For the sake of this discussion and this lab, we're going to look mainly at rotating equipment. We can also use timers to time the movement of robots or arms, to move time for pieces to be from one place to another, or for a complete process to take place. A timer can time the period of each revolution. That's what we've done with the striker and the proximity speed switch. The period is actually the seconds per revolution. That is to say, how many seconds each revolution takes. To determine the revolutions per second, we take the reciprocal of the period. In other words, 1 over seconds per revolution. 1/10 of a second is equal to 600 RPM. The standard TIM timer can time right down to 1/10 of a second, but that's to say that is the smallest increment of time it can actually measure. Therefore, the TIM has limited discrete speeds it can actually detect because of that being actually a large amount of time with respect to PLC timing. 600 RPM is the maximum speed with one striker that you can actually measure using a TIM timer. And as you can see with the chart below there are large gaps between detectable speeds. The smallest time being 0.1, which is 1/10 of a second. That's the lowest usable time that you can actually have on a TIM timer. It's at 600 RPM. At 0.2 or 2/10 of a second, that's 300 RPM. As you can see, there's actually a 300 RPM gap between those two speeds. Going to the next, what you see is a 100 RPM gap between 0.2 and 0.3. And between 0.3 and 0.4, it's narrowed down now to 50 RPM, but there is still only discrete speeds that you can actually measure. For the purposes of faster time, we can actually use an ultra-high speed timer. It times 100 times faster than the TIM, used when close monitoring of speed is needed because the time period is much smaller, 1 microsecond as opposed to 100 microseconds for the TIM, or whenever the TIM is just not fast enough to monitor the process. What we see in this slide is that the TIM-HH actually can time down to 1/1000th of a second, 1 millisecond. And that is to say that is the smallest increment of time it can measure, right? Therefore, you can actually use a TIM-HH for higher speeds because it will detect much faster speeds. If you do the math with 1/1000th of a second, the speed actually becomes ridiculous. It's up as high as 20,000 RPM for just one striker, right? There are small gaps between the detectable speeds. Shown here in the table is it's showing times of 30 milliseconds, 31 milliseconds, 32, 34, and 35 milliseconds. And as you can see, 30 milliseconds is 2000 RPM. The next one below that at 31 milliseconds is 1935 RPM, which gives us a 65 RPM gap. And as you notice, it's still, even though the higher speeds, it's a smaller percentage of gap between each speed that it can actually measure, making the TIM-HH much more useful for accurate measurements of time and speed. It's good to keep in mind the fact that the speed switch we are programming will shut the motor down if the RPM goes too low. Even though there's maximum speeds to these timers, the maximum speed of the timer is actually the lowest speed it can rotate before shutting down. Okay, that is to say, as soon as the motor rotates slower than what the timer allows, the motor will shut down. It will shut off. The ultra high speed timer, TIM-HH, times down from a set value just like a TIM. It is a 1 millisecond timer. It times in increments, obviously, of 1/1000th of a second. And like the TIM, we use the hashtag to precede the number, so we show that it isn't, in fact, a channel that what we're monitoring here, that it is actually a number. It's a BCD number. And hashtag 5 actually represents 5 milliseconds. Right? The memory, as I said here, is in BCD, binary coded decimal. When the rung is true, it times down from the set value placed in the timer. When the rung is false, like the TIM, it resets. The same as any other timer, the timer must have a unique number. No two timers can have the same number. Remember though, timers and counters can have the same number, but no two timers can. The time value, not shown in this illustration, is less than the set value when the rung is true. As soon as the rung becomes true, it starts timing down from the set value, and it is very, very fast. When that time value reaches a value of 0, the timer is said to be complete. It is complete, it is done, and the completion bit now holds a value of 1. It changes from a 0 to a 1. And the set value here is in binary coded decimal and must be preceded with a hashtag. Time adjustments can be done online by double-clicking the set value and being in monitor mode. And then you have a window where you can actually enter the set value. It must be preceded with the hashtag. The ranges are from 0 to 9,999. However, the useful range of this timer is from 1 to 9,999. 0 is not really a useful number. You might as well just have a coil having a time of 0. Takes no use of the timer's attributes. The completion flag of a TIM-HH timer is held in timer memory. It's a single bit. When the timer is complete, it goes to a 1, and when the timer is reset or not complete, the value of the completion flag is actually a 0. The flag is just a bit that signifies that an action or a cycle has been completed or is complete. The instruction address to the completion bit of a timer, as an example, the one shown on the top there, T0001, that will actually become false when the timer is completed, as opposed to the one that's addressed there as T0000. That one will become true when the timer is complete. Shown here is a double striker on a shaft. As the shaft rotates, every time the striker comes in front of the proximity switch, it reads that striker and closes. As soon as the striker moves away from the proximity switch, it opens. So what we have is a contact that is opening and closing continuously as the shaft is rotating. As you see with the two TIM-HH timers, the contact that's controlling them is addressed to the same address, really to the same switch. So the top timer actually is timing how long the switch is in fact open. The one on the bottom is the one on the second line is timing how long the switch is closed. And as long as those those timers never become complete, the third line on the bottom with their completion flags, that will become true. And as long as it remains true for a prescribed period of time, it is said to have proved that the shaft is in fact turning. As soon as the shaft is stopped in one position or the other, one of the timers will time out, the proofing timer rung will become false, it will reset, and then we can take some sort of action like shut a motor down or give an indication to an operator that in fact something's wrong with the equipment, it has stopped. Here's actually a real program taken from my computer. As you can see here, both ultra high speed timers are controlled by the same contact addressed to the same input bit, and as long as the period of time is never exceeded or reached by whatever switch is connected to it, in other words, it is opening and closing at such a rate that none of those two timers, the TIM HH, ever become complete, the bottom rung will remain true and the proofing timer will have a time to time out. The proofing timer allows enough time to actually prove that there is movement or there is motion, and that there is a constant change of on and off. And as long as the timers that are timing this out never reach completion, the on and off timers never reach completion, the proofing timer will time out. Now, it's a good idea to set the proofing time for at least 4 times the time of either the on or the off, the on or the off timer, the maximum one of the on and off timer. That gives it a couple of revolutions in order to prove that there is in fact speed, and it's not just a transient movement of the shaft or something has just moved it a bit but not continuously rotating.